Hello everyone, let's solve a very good graph problem today. We are given a graph with n nodes labeled from 0 till n-1 and n-1 edges with no cycles. Each node in the graph has a value associated with it, and we have to find the number of paths in the graph such that the starting and the end node have the same value. And we must also ensure that all the nodes in this path have a value at most equal to the value of the starting or the ending node. Let's understand this with an example. For example, if we choose a starting point to be node 0, since its value is 1, our end node in the path must also have a value of 1. Similarly, if the starting point is node 1, our end point can be node 4 because it has a value of 3. We can also have the same starting and ending point because both of them have the same value. And regarding our second condition, when we choose this node to be our starting point, even though node 2 is connected to it, we cannot go over there because its value is greater than the value of the starting node. But on the other hand, when this node is the starting point, we can go to node 0 because its value is not greater than the value of our starting point. So when we are trying to count the number of valid paths, since we have 5 nodes, we already have 5 valid paths where each node is the starting and the ending point. There's another valid path where we start at node 1 with the value 3 and we go to node 4 with the same value. In this case, all the intermediary nodes have a value less than or equal to 3. It's also given that the reverse of a path is considered the same path, so we'll only count this once. Let's try to come up with an intuitive solution for this. Let's try to understand some properties of this graph with the help of a very small example. If we consider these two nodes with the value 1 and try to find a path between them, we can see that even though there's an edge between these two nodes, we cannot travel from node 0 to node 1 because the value at node 1 is greater than the value of the starting point. Similarly, when we start at node 2, we cannot reach node 1. So node 1 behaves like a mountain that we cannot cross. But when we take value 2 as the starting and end point, because it is the maximum value in the path 1, 2, 3, we are able to travel in both the directions. So even though the graph is undirected, we can only travel through the edges in a direction based on the starting values. For example, when our starting point is a node with higher value, we can travel through that edge. So you could see that probably it makes sense to give each edge a direction from the higher value node to the lower value node. This will become clearer with the next example. Let's take a look at this example with 12 nodes and 4 different values. Since we have 12 nodes, we can at least have 12 paths with the same starting and ending points. For our remaining paths, we have to look for each distinct value to be our starting and ending point, and if the path is valid, we can count it. For example, these are the nodes with value 1. So if we are trying to form a path where the starting and ending value is 1, we have to look for a path between these 4 nodes. Similarly, when we are trying to look for a path with the starting and ending values as 2, we have to count how many valid paths we can form between these 3 nodes. Similarly, these are the 2 nodes with the value 3. So if there's a path with the starting and ending values as 3, it must be between these 2 nodes. And this is the last distinct value 4. So we have to count how many valid paths can be formed by these 3 nodes where the starting and ending points is taken from these 3 nodes. So let's count the paths with the starting and ending values as 1. Let's try to connect node 8 and node 1. Since our starting value is 1, we cannot travel from node 8 to node 3 because its value is greater than 1. Similarly, when we try to travel from node 1 to node 3, we cannot travel because its value is greater than 1. But when we try to connect node 9 and node 5, we see that there is a path between them because there are no nodes in between with a value higher than 1. So we know that these 2 nodes can be connected and there is a valid path between them. Hence we can consider them to be a part of the same group. So now we have these 3 unconnected groups and we have to count how many valid paths we can form within these groups such that the starting and ending values are 1. These 2 groups have just a single node with value 1, so we cannot choose a pair of starting and ending points within them. Now when we look at this group, we can form a path between nodes 5 and 9 in any order. So there is one valid path with the starting and ending values as 1. In general, this could have also been derived by using the fact that we have 2 nodes in this group with the value as 1 and we have to choose two nodes for our starting and ending points. It is the same as choosing two nodes from the number of nodes with value 1 in this group. So we'll add 1 to our answer. Now let's count the paths with the starting and ending values as 2. Now when we try to go from node 4 to node 1, we see that it is a valid edge because our starting value is 2 and node 1's value is smaller than it. Similarly, all these three edges are valid. So you can see that we can connect these four nodes together when the starting and ending value is 2. So we can consider them to be part of the same group. Now when we consider node 6, it cannot travel to any of its adjacent neighbors because their values are greater than 2. So we'll consider it to be a self group. In our first group, we have two nodes with value 2. So there is only one way we can choose a starting and ending points between them. So we'll add 1 to our answer. Now let's try to count the paths with the starting and ending value as 3. We see that from node 2, these two edges are valid. And when we see node 10, we see that the edge to node 5 has now opened up. So we see that our two nodes with value 3 and these two groups can now connect together. So we'll consider them to be the same group. So in this group, we have two nodes with values 3 and there's only one way to connect them. So we'll add 1 to our answer. Now let's try to form the paths with starting and ending values as 4. We can see that these four edges have now opened up. So these three nodes and the two groups can now connect together. So this will be our final group comprising of the whole graph. We have three nodes with value 4 and we have to choose two nodes for our starting and ending points. So we can do that in 3C2 ways. So we'll add 3 to our answer. So we are now done forming all the paths with all the distinct starting and ending values, and adding all of these will get our answer. So in this approach, we are starting with the smallest possible value, and then we are forming groups of connected components, and within each component we are counting the number of ways we can choose the starting and ending points, and when we are done forming paths with this value, we try to form paths for the next bigger value. And whenever new edges are being opened up, some of these existing components will connect and we'll use union find for that. The time complexity of our union find algorithm would be n into iterated logarithm of n. This part will be very small because we are using path compression for our find method. So we can also consider it to be O of n. And the space complexity would be O of n because we have to store the parent for each node. Let's implement our solution. Let's create a variable to store the number of nodes. We'll create a hash map to store the parent mapping for a union find. Since each node can individually form a valid path, we'll initialize our answer to be n. Now we'll create a mapping of all the nodes with the same value. We'll use a hash map for that where the key would be the value, and we'll be keeping a hash set for all the nodes having that same value. Now we'll create an adjacency matrix for a graph. We'll use the hash map to store that. Now we'll go through all the edges and add it to our adjacency matrix. As we have already seen, we'll keep a direction for the edges and we'll be only allowed to travel if the value of the node is greater than or equal to the value of the other node. We'll now have the same check for the other node. In that case, we'll add an entry in our adjacency matrix for the other direction. We'll also add an entry for both of the nodes in the hash map corresponding to their values. Since this is a hash set, we may be adding this entry multiple times for a node, but this will be stored only once. Now we'll define our find function for a union find. We'll first add an entry for that node if it does not exist in the parent hash map. We'll set itself to be its parent. We'll try to find the root parent of this node. So we'll continue to go upwards in the chain till our current node does not become equal to its parent node. And every time we are going upwards, we are updating its value also to the root of the chain. This path compression technique will optimize our find method. And once our current node becomes equal to the root, we'll return the root node. Now we'll implement our union function where we'll take in two nodes as input parameters. Since we do not have any specific criteria on how to merge the two groups, we'll just set the parent of the first group's root to the root of our second group. Now we'll go through all the distinct values in ascending order. So we'll sort the keys of the hash map which stores the group of nodes with the same value. Now we'll go through each node with that same value So we'll iterate over that hash set. Now for that node, we'll go through each of its neighbors. And since we have already stored the neighbors in such a way that there is a direction from the node with a higher value to the lower value, the two nodes, if they belong to a different group, can be connected. So we'll now connect the node to the group its neighbor belongs to. So we'll call union on both of them. Now we'll have to count for each group how many nodes are there with our current value. So we'll create a hash map for that, where the key would be the root of the group and the value will be the count of the nodes in the group with our current value. Now we'll again go through all the nodes with our current value. For each node, we'll find the root of its group, and corresponding to that in our hash map, we'll increment its count. So this hash map will store the root of each group in which there is a node of our current value, and corresponding to that, it stores the count of the nodes with the same value in that group. We'll now go through all the values in this hash map. Since we are not concerned who the root of that group is, we'll just iterate over the values to get the count. The number of paths that we can form in that group will be the combination of the count of the nodes with our current value and choosing two nodes from it. We'll add this to our result. And once we are done counting the paths for all our distinct values, we can return our answer. Let's submit our solution. You can see our solution is accepted. If you have any doubts or concerns regarding this solution, please mention in the comments. If you thought this video was helpful, please leave a like and subscribe to the channel for more such content. Thanks for watching.